Study about the on-chip clock generation and distribution. The clock signals are the heartbeat of digital systems. You might have heard about clock signals from many times. The ideal clock signals should have zero clock skew, specified duty cycles, minimal rise and fall time. But in reality, clock signals have non-zero clock skews, variable duty cycles, and noticeable rise and fall time. You might have heard about clock skew duty cycle many times, but still, let me define once again what is clock skew. If you see this figure, there are two D flip-flops. D flip-flop, this is one D flip-flop and another D flip-flop here. And between these two, there are some combinational logic circuits. Let us assume such a circuit. Now, for flip-flop 1, clock is applied here and same clock is applied to second D flip-flop, which is far away from it. Now what happens? Though the clock signal is derived from the same source, it arrives different circuits of the different parts of the circuit at different times. This is called clock skew. Therefore, clock skew is a phenomenon in synchronous digital systems in which the same source clock signal arrives at different components at different times. Now, at this component, it has arrived at this time, and to the second component, it has arrived with some delay. So, the difference between these two arrival times is called clock skew. So, for an ideal clock signal should have zero clock skew. We have to design circuits in such a way to have zero clock skew. And another definition that we use for ideal clock signal is duty cycle. Duty cycle is commonly expressed as percentage or a ratio. Duty cycle D is equal to pulse width divided by total time period of the waveform multiplied with 100 when we express it in terms of percent. So duty cycle is defined as the ratio between the pulse duration or pulse width and the period of a rectangular waveform. Let us see some examples. First example, this waveform has 25% duty cycle and the second waveform has 50% duty cycle. Then the third waveform has 75% duty cycle. What is this percentage? Now let us see the first waveform. 25% duty cycle means the signal is on for 25% of the total time period, but it is off for remaining 75% of the time period. Let us see the second waveform, 50% duty cycle. The signal is on for 50% of the total time period and it is off for the remaining 50%. When we come to the third waveform, 75% of the time period the signal is on and 25% it is off. Now, an ideal clock signal should have specified duty cycles. So these are the qualities of an ideal clock signal. That is, the ideal clock signal should have zero clock skew, specified duty cycles, minimal rise and fall time. You know, this is called the rise time and this is called the fall time, right? Now, with this basic knowledge on clock signals, let us see what are the techniques to generate clock signals on chip. We know in VLSI we are designing circuits in microscopic dimensions. Therefore, in this microscopic dimensions, how we generate clock signals and how we distribute clock signals is a very important task. Now, there are some techniques for on-chip clock generation. First one is using a ring oscillator. Let us see this circuit. This is a ring oscillator. Here is a ring. In this ring, odd number of NOT gates are connected. Odd number of NOT gates are connected. And here we take the output. You know, oscillator, it gives oscillations. If it is a sinusoidal oscillator, it will give sinusoidal oscillations. Now, this oscillator oscillates between 0 and 1 like our clock pulse. So to generate our clock pulse, we use this ring oscillator. So what is a ring oscillator? Ring oscillator is a device composed of odd number of NOT gates in a ring whose output oscillates between two voltage levels representing true or false, 1 or 0. This type of oscillator is predominantly used in low-end microprocessor chips. Now here we get clock pulse, I mean the output of the ring oscillator, and when we take one inverted output, we get clock, and a double invert, you get clock pulse. Now let us see this also with an example. And this is a gate question that we have seen in previous gate question papers. And you see, this is a ring oscillator. This is a ring oscillator. And ring oscillator is designed with odd number of NOT gates. Therefore, here, how many NOT gates are there? 5 NOT gates are there. So, for such a ring oscillator, for the ring oscillator shown in figure, the propagation delay of each inverter is 100 picoseconds. Propagation delay, the time taken for the gate to propagate its input to the output is called propagation delay. We have defined this propagation delay several times. Now, when each inverter has propagation delay of 100 picoseconds, 5 such inverters are connected like this in a ring oscillator. What is the fundamental frequency of the oscillator? So you have to calculate from the given information the fundamental frequency of the oscillator. So what are the answers? A 10 megahertz, B 100 megahertz, C 1 gigahertz, D 2 gigahertz. So from this given information, how do we calculate the fundamental frequency of the ring oscillator? Now you just see when we give input, at the input, if we assume at the inverter input, if we assume 0 is at the input, because odd number of inverters at the output of the last inverter, we will have 1 as its output. So that means how this 0 is propagated to 1 with 100 picoseconds delay. Now this 1 is translated into 0 from at the output of this second inverter after 10 picoseconds. And again, this 0 is inverted to 1 after 100 picoseconds. And another 0 after another 100 picoseconds. Again, after another 100 picoseconds, it will be changed to 1. That means from 0 to 1, the output of the oscillator, it is taking 500 picoseconds time. So therefore, now when this 1 is applied at the input of the first inverter, and this 1 is made to 0 after second 500 picoseconds. Therefore, here you can see 0 is made to 1 within 500 picoseconds, and one is made to 0 with another 500 picoseconds. Now, from here to here, we call it as a time period. Otherwise, from here to here, we call it as a time period. So, the total time period is equal to 500 picoseconds plus another 500 picoseconds. Total time period is equal to 1000 picoseconds. 1000 picoseconds. 1000 10 power 3 picoseconds 10 power minus 12. So it is equal to total time period is equal to 10 power minus 9 seconds. Now when we have time period of a waveform, we can calculate the frequency. So frequency is equal to 1 by time period. So 1 by 10 power minus 9, it is equal to 10 power 9. So the fundamental frequency is equal to 1 gigahertz. 1 gigahertz. So 1 gigahertz answer is C here. I think you have followed the given problem. So like that, if a ring oscillator is given and with the help of propagation delay, we can calculate what is the fundamental frequency. Now, another circuit to generate clock pulses on chip clock signals is using a Pierce crystal oscillator. What is a Pierce crystal oscillator? This is almost a crystal oscillator, what we have studied. It is the derivative of a Colpitt's oscillator. You have seen sinusoidal oscillators, Colpitt, Hartley, like that, so many sinusoidal oscillators we have seen. So this Pierce crystal oscillator is also a derivative of Colpitt's oscillator. Here you can see the crystal. Crystal is used as oscillator, and this crystal can be represented as a series RLC circuit. And series RLC circuit, you know, frequency of oscillations F is derived as F is equal to 1 by 2 pi root LC. That means when we say R, L, and C, when inductive reactance XL is equal to capacitive reactance, resonance occurs. So when XL equal to XC, we get F is equal to 1 by 2 pi root LC. So up to this we get sinusoidal oscillation. Now here we connect another Smith inverter. That means it is another inverter. Now this Smith inverter converts this sinusoidal signal into square wave. For your on-chip clock pulses, clock pulse, we should have a square wave. That means with 50% duty cycle. So this is another circuit which is used to generate clock pulses on chip. Then let us see another circuit which can derive from one single clock pulse to non-overlapping clock pulses. This is a simple circuit that generates a pair of non-overlapping clock signals from a single clock. This is the clock. This is the clock signal. Now, with this single clock, we can generate two non-overlapping clock pulses. This clock pulse is different and this clock pulse is different. Let us see this circuit arrangement. At the clock input, let us assume it is designed with this circuit arrangement, and what is this, NOR gates, and with one NOT gate. When clock is equal to 0, what happens at the input of the NOR gate? We will have 0. At this input we have 0. Let us assume other input to this NOR gate as 1. Now this input is 1 and the clock is 0. 0 plus 1 is 1 at the OR gate, 1 bar for NOR gate. So 1 bar is equal to 0, and therefore this is equal to 0. Let us see once. Clock is equal to 0. This clock is given here. And phi 2, that is second input, is also equal to 0. Sorry, previously I have mentioned reverse manner. One clock is equal to 0, and Let us assume that another input to the NOR gate is equal to 0. When both inputs to the NOR gate are 0, 0 plus 0 bar, that is 1. Therefore, clock is equal to 1 as shown here. Right? So, clock is 0, phi 2 is 0, and therefore, phi 1 is 1. So, like that, one clock is generated. Right? Now, this phi 1 is applied to the input of second NOR gate. Now, this is 1. When this input is 1 and clock is 0 earlier, and that clock is inverted at the input at the inverter, and therefore it is 1, right? So this is 1 and this is 1. 1 plus 1, 1 bar not get 0, therefore phi 2 is 0. So what we assumed phi 2 is 0 is correct. So this is the first condition. Clock is equal to 0 and phi 2 is equal to 0. When these two are 0, we get clock 1 is equal to 1. Let us take second example, second part of the clock pulse. Clock is equal to 1. When clock is equal to 1, input of the NOR gate is 1 here, right? When this is 1, let us assume phi 2 is equal to 1 and both are 1. 1 plus 1 for OR gate is 1, and because it is an OR gate, it is 1 bar, it is 0. So therefore, you can see 1 and 1, 1 plus 1 is equal to 1 bar, it is 0. Therefore, phi 1 is equal to 0. Phi 1 oscillates between 1, 0, 1, 0 like that. Similarly, phi 2 oscillates between 0, 1, 0, 1 like this. So this is another circuit arrangement that generates a pair of non-overlapping clock signals from the single clock. And this is another circuit. Using clock decoder circuits, we can generate different clock pulses. Right? Now, clock, this is the symbolic diagram, symbolic representation of a clock decoder. And these are some sample waveforms I have shown here. And this is the gate level implementation. Right? Now, let us see clock decoder, which decodes from 2 to many. So, clock 2, 3 and clock 3, 4 are the input signals. And now it is decoded as clock 1, clock 2, clock 3 and clock 4. Let us see what is clock 2, 3. Clock 2, 3 means this is 1, up to this it is 1, then 2 and then 3 and then 4 parts. You can see here, first part of the clock, then second time period, third and fourth. So clock 2, 3 means what? 2 and 3 are high and 1 and 4 are 0. Let us see clock 3, 4. Clock 3, 4, 3 is high and also 4 is high. So this is clock 3, 4 and this is clock 2, 3. I think you have followed. Now let us see what is clock 1. Clock 1 means first part of this clock is 1 and all others are clock 2 is 0, here clock 3 and 4, these are 0. So this is clock 1. Then what is clock 3? This is clock 3. Where 3 is 1, it is called clock 3. Right? Now let us see with the clock 2, 3 and with the clock 3, 4, how we can generate clock 1 with the gate level implementation. This is an OR gate. Clock 2, 3 is applied here and clock 3, 4 is applied to the other input of a NOR gate. Now clock 2, 3 is this, clock 2, 3 is this, and clock 3, 4 is the second waveform. Now when these two waveforms are NORed, what is the output of the NOR gate? Now this is 1 and this is 0 and therefore what happens? It will be 0, right? because 1 plus 0 is 1 and bar, 1 bar, it is 0. Now let us take this part. Clock 2, 3, 3 part and 3. So 3 and 3 both are 1. So 1 plus 1 is 1 OR gate, and because it is an OR gate 1 bar, so it is 0, right? And this part is 0 and this is 1, and 1 plus 0 bar is 0. Therefore, for all these time periods, clock pulse is 0. Now let us come to this part. It is 0 and this is 0. 0 plus 0 bar is 1. Therefore, when we apply clock 2, 3 and clock 3, 4 to a NOR gate, we get clock 1 as the output. So like that, we can generate different waveforms. That means clock 1, clock 2, clock 3, clock 4. Now here also you can see how clock 3 is generated with this gate level implementation. Clock 2, 3 is this and clock 3, 4 is this. Now there is a NOT gate connected here. So when it is inverted, how do we get the output? That means clock 2, 3 is not of clock 2, 3. What we get, and not of clock 3, 4. What we get here, let us observe. Right. Now let us see this first one. Clock 2, 3 is this, and this is 0, and this is also 0. So 0 is made 1, and this is made 1. So 1 plus 1 is 1 bar, it is 0. So therefore, this is the bottom waveform we get. Now let us come to the next one. 1 bar is 0 and 0 bar is 1, right? Now 1 plus 0 bar is 0. Therefore, we get 0 here, right? Now again, you see the last one also, right? This is 0 and this is 1, and this 0 is made 1. Sorry, right. This 0 is made 1 and this 1 is made 0 because of the presence of NOT gates. Therefore, we get 1 plus 0 bar, 1 bar is equal to 0. Now let us come to this part, right? 1 is made 0 and this 1 is made 1 because of the presence of NOT gate at the input. Therefore, this is 0 and this is 0. 0 plus 0 is 0 bar. So 0 bar is 1. So like that, we can generate clock 3 with this type of gate level implementation. We thank Zoom people. They have given a bonus time for our lecture. Right? I think you have followed this clock decoder, and this is a symbolic diagram of clock decoder. And these are the two clocks that we apply at the input, and we can derive these clocks. This is one circuit arrangement. Now, the clock signals, they are very important in designing our VLSI circuits, and these clock signals are required almost uniformly over the entire chip area. Therefore, it is desirable that clock signals are distributed with a minimum delay. If there is delay, we say there is clock skew. So we like to have zero clock skew in clock circuit, clock generation, digital circuits. Therefore, in order to have zero delay or uniform delay, this is the circuit arrangement. That means this is called a H-tree clock distribution network. This is the clock generator. We have seen ring oscillator and Pierce crystal oscillator, like that. So from various clock generators, we generate a clock, and after that, to various parts of the circuit, we have to distribute clock. So if we maintain at least uniform delay, we will have proper signal output without glitches. And now let us see, this is H distribution, and it is distributed like this in the form of H, right? Again, it is distributed to other circuits in the form of H. So therefore, we call this arrangement as H-tree clock distribution network. So this is a ideal distribution network, and this is, but however, it is very difficult to implement it in practice, because in order to have fan out requirements, this is not that much advisable. Now, let us say another circuit which suits our large fan out requirements or high fan out requirements. It is a three-leveled buffered clock distribution network. So this is the clock source, and three levels clock distribution is taking place at three levels. It is called a three-level buffered clock distribution network, right? So it is also essential that every buffer stage drives the same number of fan out gates so that the clock delays are always balanced. So like that, we have different clock generation and distribution networks. While designing these VLSI high-speed VLSI circuits, we have to remember few things. Let us see what are the important things that we have to remember. Ideal duty cycle of a clock signal is 50%. So we have to generate a clock signal with an ideal duty cycle of 50%. Okay? Then, to prevent reflection in the interconnection network, the rise time and the fall time of the clock signal should not be reduced too excessively. That also we have to keep in mind. Then, the load capacitance should be reduced as much as possible. And we also have to remember that inductive loads can be used partially to cancel the effects of parasitic capacitances of a clock receiver. Then there should be adequate separation should be maintained between high-speed clock lines in order to prevent crosstalk. That means adequate separation should be maintained between high-speed clock signals in order to prevent crosstalk. Actually, crosstalk is a term we come across many times in the communication. Here also, to prevent crosstalk, we have to maintain separation properly, right? And also, placing a power or ground rail between two high-speed lines can be an effective measure. This we have to keep in mind. So I hope you followed today's lecture. We have seen what are the various on-chip clock generation and distribution networks, and we have seen the requirements of ideal clock signals, that is zero clock skew and reduce minimal rise and fall times, and duty cycle, variable duty cycles and all. And we have seen what is the duty cycle and what is the clock skew. And then we have seen a ring oscillator, and we have done a small simple problem. And then we have seen a Pierce crystal oscillator. Then we have seen some one circuit arrangement which can derive non-overlapping clock signals from original one clock signal. And then we have seen clock decoders and how H-tree distribution network is used. And then we have seen three-level buffered clock distribution. And then finally, we have seen what are the points that we have to remember while designing high-speed VLSI circuits, right? With this, I can say I could reach you through this online lecture. If you have any doubts, don't hesitate to ask me. We will have some 5 to 10 minutes time for our interaction. And before that, one point I want to tell you. So this is my website, and I have created this website for you only to meet you people. So you visit my website and you can get the slides and our the material, whatever you expect from me, I will post here. Therefore, you try to get slides from my site. You please note down this, and I will also share this link through your WhatsApp group. And as you know, whenever I cover about a topic, I will mention the textbook, what I have referred. So this is the textbook that is mentioned in our syllabus from JNTUK, that is CMOS, Digital Integrated Circuits, Analysis and Design, this foreign author, right? So now I thank each and every one of you for your patient listening.